Welcome friends. Now we are going to start with the next topic in this arc welding, that is the heat flow characteristic. Okay. So basically the study of this heat flow characteristic will provide us the minimum estimate of the heat input rate required to form the weld of a given width. Okay, now if you look at the fusion welding techniques, so here the source is moving whereas the work is stationary. Except you talk about the resistance welding, there is a source which is stationary and work is moving. So in such a case, if once the steady condition is reached, then even the source is stationary, the temperature distribution related to the source will be the uniform. Okay, now to analyze such a problems, what we are considering that the source is stationary and the workpiece is moving in the opposite direction with the same velocity, and that velocity or speed is nothing but the welding speed. Okay, so the most convenience method of analyzing so this kind of problem can be done in the two cases. There are two steps, or there are two kinds via we can able to analyze these problems. Okay, so in most of the cases, so here the heat source is idealized as the small zone. Okay, and that small zone we can consider as a point. Okay, so here the heat is liberated at a point, and the heat flow in that point we can call it as a three-dimensional heat flow. Whereas suppose if you take a case of a butt welding, so where the thin plates are there but the lengths are huge, so in that case the heat source can be idealized as a line. Okay, and that kind of heat flow, it is known as the two-dimensional heat flow. Okay, so the thing is that here we are having two kinds of the sources, power sources. One we are idealized as a point source and another as a line source. So I can show you the diagram. Say I am idealizing the point source. This is X, this is Z, this is Y. This is the velocity of weld. Then here, see, this is a point source, and here the temperature as a function of X, Y and Z. Okay, so this is three-dimensional. Okay, we are assuming it as a three-dimensional heat flow. And in the second case, so where now the very thin plates but the length is more, for that we can considering it as a line source. This is X, this is Z, and we are considering as this is a line source. This is Y, and this is the velocity of weld. V is the velocity of it. This is the line source. This is the line source, and here the temperature is a function of X and Y only. It is a two-dimensional heat flow. Two-dimensional heat flow. Whereas this is three-dimensional heat flow. Okay, so what we are going to find is that the heat input rate, okay, in three-dimensional heat flow and in two-dimensional heat flow. So the heat input rate, the heat input rate for the three-dimensional heat flow is given as, say, Q is equal to 3.93 into K theta m into W into bracket 2 by 5 plus VW divided by 4 alpha. Okay, where Q is what? Our heat input rate in watts. K is the thermal conductivity of the plate material. Thermal conductivity of plate material in watt per meter per degree centigrade. Okay, then we are having W is a width of weld. V is the velocity or speed of welding. It is in meter per second. And alpha is thermal diffusivity in meter square per second. Okay, which can be given as K divided by rho C. Okay, K is thermal conductivity of the material, rho is the density of the material, C is the specific heat. Okay, this is the heat input rate which is given for the three-dimensional heat flow characteristic. Okay, at the same time we can have the heat input rate for the two-dimensional heat flow, that is given as 8 K theta m times H into bracket 1 upon 5 plus VW divided by 4 alpha. Again, and theta m in both the cases, this is the temperature above the initial temperature up to the melting point of that material. That is, you can take theta m as a temperature difference from melting point to the room temperature or whatever the initial temperature during the welding process. Okay, now here is same also, where H is here is the thickness of the plate. We are taking H here what? Thickness of the plate. Remaining all parameters are same as like that. K is the thermal conductivity, theta m is the temperature above the initial temperature up to the melting point. V is the velocity or speed of welding, W is the width of weld, alpha is the thermal diffusivity, and H is the height of plate or thickness of plate you can take. So these are very important relations for the heat flow characteristic for three-dimensional heat flow, and this is for two-dimensional. This is for 2D heat flow and this is for 3D heat flow. Okay, so we will take one example so that you can get the idea. So again, in the arc welding, where the heat input rate with the metal transfer is given as Q is equal to C into Vi. Okay, so where V is a voltage, I is a current, and C is what? C is the fraction for how much time the arc was on. This is a fraction for time. For that time the arc in the arc welding was on. This is a fraction of time. This is a fraction for time. That is for how much time your arc was operating on. Okay, so let us take one example so that you can get the idea how to solve the numerical by using these 3D or 2D heat flow characteristic. Okay, so students, let us see what is given in the question. So in a butt welding process by using arc welding, the arc power is found to be 2.5 kilovolt ampere, that is kilowatt. the process is used to weld steel plates each of 3 millimeter thickness. That is very thin plate and butt welding is there. So definitely you can assume it is a two-dimensional heat flow. As shown in the figure, see, these are 3 millimeter plates. This is your weld and this is a groove angle is given. Okay. So determine the maximum possible welding speed, and it is assumed that the metal transfer is of short circuit type and the arc is on for 85% of the total time. So this is a fraction C is given. Okay. And these are the properties are given for steel. That is, thermal diffusivity is given as 1.2 into 10 to the power minus 5. Thermal conductivity for steel 43.6. Melting point for steel is 1530 degrees centigrade, and room temperature or ambient temperature how much? 30 degrees centigrade. Okay. Now I will rub this and then we'll solve. Okay. So see what is given here. They have given with the weld preparation. Groove is V groove. Okay. This is A, B, and of course AB is what? The width of the weld, W. Okay, if this is 60 given, so this groove angle is 60, so here is 30 and here is 30. Okay, so this is how much? 3 millimeter is given. Okay, now we have to calculate what? This is the width of the weld, isn't it? So for that, what we can do? We are having this as 3 millimeter. This is our angle 30 degree. So we can have this tan 30 is equal to what? Say this is X. So X opposite side divided by adjacent side. So divided by 3. So X is equal to 3 tan 30. So how much it is? 3 tan 30. It's 1.73. And total width will be 2x, isn't it? So width will be 2 times x, that is 2 into 1.73, that is 3.46 millimeter. Okay, now this is what? A butt joint, very thin plate. So we are assuming it is a two-dimensional heat flow case, yes or no? So for this, what is the formula for that? We know formula. This Q is equal to 8K theta m into H into bracket 1 upon 5 plus VW divided by 4 alpha, isn't it? So सबसे पहले हमको क्या निकालना पड़ेगा? Q निकालना पड़ेगा, isn't it? We have to find this velocity. So Q is given like that. Q is equal to C times VI, and fraction कितने समय के लिए ऑन थी? Arc, that is 80%, is it 0.85 into voltage is how much? Directly rating is given as 2.5 kilovolt ampere, that is 2.5 into 10 to the power 3. So how much? 0.85 into 2.5 to the power 3, it is 2125 watt. Okay, so we got here the value of Q, isn't it? Now theta m is how much? Theta m, so it is temperature difference from melting point to the ambient. 1530 minus 30 degree, so it is 1500 degree centigrade. Okay, now let us, first of all I will calculate this value so that it can be easier. So what is this? Q divided by 8K theta m into H, isn't it? minus 1 upon 5 is equal to VW divided by 4 alpha. Put the values. So Q is how much? 2125 divided by 2 times what is value of K? So thermal conductivity 43.6. 43.6 into this theta m 1500 degrees centigrade into height. How much? It is 3 millimeter. Okay, so I will take that 3 into 10 to the power minus 3 meters. Okay, so just check this is correct or not. 0.85 into 2.5 e to the power 3, 2125. Right, correct. After solving, minus this 1 by 5 VW by 4 alpha. Let us solve this for VW by 4 alpha and tell me what is the value for VW by 4 alpha. Do it. So you will get this VW divided by 4 alpha as 1.05. Please check. Okay. Now we are interested in finding out the velocity they are asking. Okay. So V will be 1.05 into 4 into how much the thermal diffusivity is given? It is given as 1.2 into 10 to the power 1.2 into 10 to the power minus 5 meter square per second divided by this W. How much W we have calculated? It is 3.46, isn't it? 3.46 into 10 to the power minus 3. It will be in meters. So what is velocity? If you calculate 1.05 divided by answer into e to the power 3 into 1.2 e to the power minus 5. So it is around 1.05 into 4 into 1.2 e to the power minus 5 divided by 3.46 divided by e to the power. So it is 0.0146 meter per second. So this is the thing they have asked. So what is the speed of welding? So speed of welding will be how much? 0.0146 meter per second. So many times what they will do in the gate examination, they will provide you the equation for the Q. Okay, once they have asked the question in gate examination, they have provided the formula that we given 8k theta m into h into bracket 1 by 5 plus VW by 4 alpha, it is given. So just understand how to solve this question based on heat flow characteristic. Okay, thank you.